In this video, we're going to talk about surfaces like these ones. We're going to try to describe them mathematically in implicit, explicit, and perhaps most importantly, parametric forms. In future videos, we're going to talk about things like what is the surface area of a surface, what is the surface integral analogous to the line integrals we've seen before, and we're going to ask the question of, well, what would I do if I have a vector field combined with a surface? But in this video, we're just going to describe them mathematically. Now, to be clear, I'm only talking about the outside of these regions. I'm not imagining any interior. That is, I'm sort of imagining like it's just the surface of the Earth and I'm walking along the surface of the Earth where I could go north, south, or I could go east, west, or a combination of those, but there's really only 2 degrees of freedom when you're walking along the Earth. I'm not talking about the inside of the Earth at all. And so what makes a surface is the fact that it can be described in some sense as having sort of 2 different dimensions in which you can walk, despite the fact that it's this larger embedding in a 3-dimensional space. We'll be a bit more precise about what we mean by that in a little bit. Now, the first thing I want to do is actually go back to the study of curves that we've done before, because we've seen that for a curve like this is the top half of the unit circle, that there's actually 3 ways that we can describe this. We can describe this implicitly. So this is when I just give some function of x and y and set it to be a constant. In this case, x squared plus y squared is equal to 1. I could solve it explicitly, which is when I take my formula and I try to solve it for one of the variables, like y is some function of x. In this case, square root of 1 minus x squared. And I chose specifically that we were only doing the top half of the unit circle because then I can solve it. I don't have any weird plus or minus issues coming up. In general, though, it's often not possible to start with an implicit formula and to generate just a single explicit formula for it that works for everything. This in general is not possible. So it's only sometimes that I would have an explicit formula for my curve. And then the third, and the one that's going to be most important for us, was the parametric form. This is where I take some parameter t, and then I specify some function in the I hat, in this case it's cosine of t, some function in the j hat, in this case sine of t. And whenever I come up with a parameterization, I always have to specify the endpoints of my parameterization. So in this case, I'm going only half of the circle, and so t is between 0 and pi. So that was for the specific example of a half circle. If I'm going to be just a bit more general, the implicit formula is just some function, capital F of x and y equal to a constant. The explicit is when I can solve it so that y is equal to some function, lowercase f of x, and then the generic parameterization is just some position function r of t, which is just a function of g of t in the I hat, a function h of t in the j hat, and t bounded between a and b. Okay, so let's use that base for trying to now study surfaces in 3 dimensions. So I'm thinking about a 2-dimensional object embedded in 3 dimensions. So it could be the case that I have an implicit description of this. That'd be the exact same type of thing we've seen before. Capital F of x, y, now, and z is equal to a constant. It might be that I could solve this for z, so z is given as a function of x and y explicitly. That sometimes can be the case and sometimes can't be. And then, most importantly, is the parametric formula. Now I'm going to have 2 parameters. So I'm thinking of surfaces as a 2-dimensional object, so there's 2 degrees of freedom, so I have 2 parameters, and I'll call them u and v. And then because it's living in 3 dimensions, there's an I hat, a j hat, and a k hat component, and each of those functions depend on the parameter. So it's an f of u and v in the I hat, a g of u and v in the j hat, and an h of u and v in the k hat. And then just the same as we've seen before, I have to say, well, what are the limits of my u and my v? So u is going to generically go between an a and a b, and v is generically going to go between a c and a d. Okay, so let's see an example. I want to talk about the cone. That one way to think about this is just taking some line and rotating it around to make this cone, but I have an explicit formula for it. Z is the square root of x squared plus y squared. Now, whenever you have an explicit formula, it's actually completely trivial to get an implicit formula as well. You just subtract off. So the implicit is just z minus square root of x squared plus y squared equal to 0. We haven't done anything at all. Here, the z minus square root of x squared plus y squared just is the capital F of x, y, and z we've seen before. So the point is, if you have an explicit, you can always get to an implicit. If you start with an implicit, reversing that process and trying to get an explicit is often just not possible. And even when it is possible theoretically, it's often not easy to do. So implicit to explicit is hard, but explicit to implicit is just trivial. So for the parametric form, I need to come up with a choice for u and a choice for v. I have an x and a y already, so what if I just do that? Why don't I, if I set it to be the parameterization of x and y, in which case the x component is just x, the y component is just y, and then the z component, because it's described as square root of x squared plus y squared, I just put in square root of x squared plus y squared k hat. So this is perfectly fine from the perspective of have you found a parameterization, but it's actually not that useful. What I really am going to want to do is come up with parameterizations that nicely capture the symmetries involved in whatever the surface was. And there is some symmetry. There's this sort of circular symmetry to a cone that is just sort of ignored by this choice of parameterization. And this is going to be a real problem for us later when we actually want to do things like compute the surface area of this. And this parameterization is going to have some really messy square roots and integrals. It's going to be a whole mess. So I'm in fact going to get rid of the implicit formula I had before because it was sort of trivial. And then I'll also get rid of that canonical parameterization that you could always do if you have an explicit formula, but might not be very helpful. And we're going to try to come up with a better one. So first thing, I'm going to put up a sort of cylindrical coordinates, if you will, on this picture. Basically what I do is I take a point on the cone and I project it down to the xy plane. Then I get some vector going from the origin out to the spot where it projects down, and that has a length of r. So r is defined to be that particular length. And then there's also an angle of theta that starts at the positive x-axis and rotates counterclockwise until it hits that line, the line we've labeled of having length r. Because my explicit formula was z equal to square root of x squared plus y squared, could have been anything, but that's what I've chosen. This happens to be the exact same thing as r. R is defined when you're talking about polar coordinates as the square root of x squared plus y squared. This is just r. So the point is, if you know the theta and you know the r value, you know exactly where you are on the surface because theta and the r is enough to describe a point down on the plane. And then if you want to know how high up you should be, what the z value is, well, whatever your r was, that's what the height is as well. Z is equal to r. And so we only need a theta and an r, and as a result, I can say my parameterization is the position vector r vector. There's two r's here, one with a vector hat and one without. So the position vector is a function of the two parameters, r and theta. And, well, we do exactly what we've done any number of times when we've talked about polar coordinates in the past. We've gone and said, well, the I hat is our cosine, the j hat is our sine, but what we're adding now is the k hat component, which is the height, which would normally be z, but since z is equal to r, it's plus r k hat. And so if you know the r and the theta, we can describe where you are on this cone. Note that this is in slight contrast to what we might have done when playing with cylindrical coordinates in the past, where we would have had a theta and an r and a z, all three of them floating around, and we would have had a triple integral that used all three of those variables if we were computing, say, the volume of a region in cylindrical coordinates. That's three-dimensional. Here we're trying to describe a two-dimensional surface. And so basically what you do is you're choosing two of the three dimensions, r and theta, which is enough to describe everything because we have that hook, that relationship that z was equal to r. And so a third variable isn't needed to describe this here. Theta and r is enough. Now I have to be careful here because I've been a little bit coy with you thus far. I said it's a cone, but which specific cone? Because what is the height of that top off where it stops graphing it? I actually told it to stop graphing at z less than or equal to 3, so I'm going to put that up there. Z is less than or equal to 3 is a restriction on my formula, so it's only that portion of the infinite cone that it would be if you didn't have the restriction. Okay, so how does this translate into r values and theta values and the restrictions on those? Well, z is equal to r. Z is clearly positive here, it's a positive square root. And so what we have is that r is between 0 and 3 as well. And then theta is one revolution around, it's the entire revolution, so theta is between 0 and 2 pi. And indeed, whenever we try to write out a parameterization, we additionally want to describe the boundaries on the parameters, in this case on the r and the theta. The final way I'm going to think about this is, okay, let me just look at my cone. I want to imagine this as some sort of transformation. There is a two-dimensional space that has axes r and theta. And in that r theta coordinate system, the region is very simple. It's just a rectangle. The r value is going between the 0 and the 3, and the theta value between the 0 and the 2 pi. It's a simple region in that coordinate system. And then what a parameterization really is a transformation from the simple region that I have, the r theta two-dimensional region, to this more complicated two-dimensional region that is the cone embedded in 3 dimensions. The parameterization is just a way to map between this simple space in the r theta plane to this more complicated situation. And because I've chosen natural parameters that reflect the underlying geometry, we're able to really simplify the process. And we'll see how that works in a little more detail coming up in future videos.